My name is Pranav, and today I'd like to talk to you about what I've been exploring, trying to play around with Swift algorithms. Um, Swift algorithms is a package which Apple released late October last year. So I'll go straight into it then. So algorithms themselves, you may be wondering, what exactly is an algorithm? You can think of an algorithm like a detailed recipe for how to write a function. Donald Knuth calls a recipe a set of instructions. So with that definition, you can think of pretty much every Swift function as an algorithm. What is Swift algorithms? Swift algorithms is a new open source package of sequence and collection algorithms. And they have lots of new data types, which help you with optimizing for performance for common operations. And with Swift algorithms, you don't need to know the nitty-gritty, like how the algorithms are actually implemented. So that's really helpful. And while there are lots of algorithms which you could use, this package is just for the most practical ones. So because the content's so vast, I'll only mention some functions that could be useful for everyday iOS dev. A bit about the package itself. So it's a new evolution format for exploring experimental features. So Apple was getting lots of long discussions on the Swift forums. So they wanted to iterate quickly and get improvements faster by making it a package which most people can contribute and raise issues on the repo themselves. So it's just faster, and they're trying it out. They've tried it out with Swift numerics, and now this one, which is the Swift algorithms. Okay, so why should you care? You don't have to reinvent the wheel for known algorithms, like I said. Swift is still behind languages like Python, especially for algorithms and other libraries. So Swift is trying to bridge this gap with new functions and new data types. The package contains highly efficient and safe code, and it's getting better all the time. For an iOS dev, writing efficient and safe code is now more straightforward, and it's easier to read. So easier to write, easier to read. And it's also really good for avoiding hidden traps in your code. So if you write an algorithm, there are lots of things which could go wrong. And I'll share an example of a hidden performance trap, which I found when I was trying to do some like a common operation. So I call the mistakes where you have a correctness trap, where you implement an algorithm incorrectly. That's a correctness trap, and a performance trap, which is like, it's not very efficient. Right, so let's go into our first demo. So I'm going to open up Xcode in a bit, but first I'd like to show you a bit about the problem. Okay, so this problem is the four-sum algorithmic problem. The problem is to return all combinations of numbers in an array that add to a given target. So let's say you have a target of 0 and an array of 1, 0, -1, 0, -2, 2. So that's a collection. And you want to return a set containing, so you want the set of all combinations of 4 numbers which add up to 0. So in this case, you'd get a set of -2, -1, 1, 2, -2, 0, 0, 2, -1, 0, 0, 1. And if you want to make sure that the algorithm doesn't take too long, you can also add constraints. So to make sure that you don't have too much memory which your computer can't handle. Even if your algorithm is really efficient, sometimes you have to put constraints on the input size and the values themselves. Okay, so with that explanation, I think I can go straight into the code. Right. Oh, actually, before I do that, I'd like to give a bit of background about how you'd actually approach this problem. So when I'm thinking about an algorithmic problem, I always think about big picture concepts. I think it's really helpful to understand what you're doing because it can get very, very detailed and very tricky really quickly. So I looked up a technique called divide and conquer. And the idea behind that concept is to solve a big problem by breaking it down into smaller subproblems and using those subproblem solutions to solve the bigger problem. So in this case, the main idea which you're trying to implement for a good solution, which is the most efficient, you want to have a solution for a pair of numbers which add up to 0. So you want to find a pair of numbers which add up to a target number. And then you want to use that solution or those set of solutions to find a triplet of numbers. And finally, you use the triplet of numbers to solve for the quadruplet of numbers. So that's a high level what I'm trying to do with the code. And the main idea is to use big O notation to represent how efficient the code is. So I'll go into a bit more about that later, but that's just some context to help you understand the code because it is quite detailed. So with that, let's look at the code. Okay, so I've opened up question 2 here. This is question 2. Okay, this is question 1. Right, so let's look at the code. So if you look at this code, you can see that the base case we've got is 2sum. So this is what we're trying to solve first. So we have an array of numbers, which is the original array. You have a target number, which is a parameter, so it can vary. And you have a start, which is like your starting index. Okay, so what does this code do? So another thing I should say is the code looks complex because you're not simply generating all possible pairs of combinations. It's an optimized way to generate the possible pairs. So rather than iterating through an unsorted array and then finding all the pairs like that, which is quite inefficient, what I've done first of all is I've sorted the array. So I've used a really simple function, .sorted. So you input an unsorted array, you sort it, and then you call the ksum, and then ksum calls 2sum when you get down to the base case. So that's like that's why you need to have a base case, so you can break down the problem, a big problem, into this simple function. Okay, so let's look at what this code is doing. So we've sorted the array. This takes O of n log n, which means that for an array of size n, it grows with the factor of n log n as you increase n. So that's quite efficient if you implement the sorting algorithm efficiently, which is efficient because we've used the Swift standard library function. And we're using a sliding window. So this only iterates through the array once. So you can see this because we've only got one while loop. So this is one array and we've only got one while loop. So we're just iterating through it once. And low is one of the panes of the window. So I think of it as a sliding window. You've got one pane, which is the minimum value, which starts at the start index for a sorted array. And then you've got the highest value, which is the highest index, which is the end of the array. In this case, it would be nums.count -1 or nums.end index -1. And then you've got the results array, which is this one. And this is going to be all the possible pairs of numbers which add up to the target for this nums array. So that's this starting stuff. That's what this does. So once we've got that, we go through this while loop and we say, what is the sum of this index value and this index value? If the sum is less than the target number, we know that all the elements below that value are less than that value. So we have to choose the number after the lowest pane. So we increment the index by 1. And then if it's greater than the target, then we move the maximum window pane down 1 index, because that's the next highest value. So that way it's quite systematic. So it's very, very definite, like you will get all the combinations doing this. And these are just some safety checks. So I've checked that the index is valid, and we don't repeat work for the same repeated elements. So once you've done that, you've checked it's less than the target, it's greater than the target. If it's not either of those, that means we've got a match. So once we've got a match, we append that to the results and we increment both panes. And because we're while loop is only one time, once you get to the crossover point, which is where the two panes overlap each other, that means that we've gone through all the combinations and we can return the result. Okay, so that is very hard to read and write. And then you can see that once k-sum is there, even this is quite complicated. We've got so we have to check if the solution is even possible for a sorted array. If the number of elements is that much, and if you know the number of elements and you know the minimum value, that means that k of those, so yeah, it's just saying that it's an optimization to save computate, like you don't want to calculate if you know you can't have a solution. And then this is k-sum. So if you have k equals 3, so you start with k equals 4, and then it goes down to k equals 3, but you just go through each index in the nums array, and you go through each k-sum solution and you append the results. And then because this is k-sum equals 4, it will iterate with k value minus 1, which means it will be now k equals 3. So for every possible k-sum for k equals 3, it's going to give you a solution. And then you basically target minus that index. So you know you have this value, and you've appended that to the solution. And then you append the sequence, which is the remainder of the solution, after you've got the k-sum calculated. So that's how this works. It's quite complicated and it's quite nested as well. You can see I've got 1, 2, 3, 4 levels of nesting. It's quite hard to read. And this is the iterative solution. So this is actually the most efficient one, memory-wise and runtime-wise, because you don't have lots of recursive calls which add more functions on the call stack. So every time you call a function on itself, it's less efficient. So what I mean by it's iterative is because to-sum is iterative. So that's a smart optimization. Okay, and then question 1, solution 2, that is the algorithms one. So this is the Swift algorithms one. It's really, really easy to read. Like you can just look at it and it just makes sense straight away. So you just read it, and so you can see like this one, you look at the algorithms function, which is dot combinations of counts. So that is not optimized, but it's really easy to understand. All the combinations in that array of count 4 filter all the combinations which add up to the target. So this is basically a way to calculate the sum of an array. And I've labeled this unsafe. I'll get back to that why I've called it that later. But this is a safe array where I've calculated the sum in a different way. Okay. So actually, if you look at this, you'd think it looks really nice. It's really clean. It looks great. Ship it. you think that's easy, that's going to work, but it's actually not efficient. So O of n to the 4, because you're calculating it without the two-sum optimization. It's a small optimization, but it makes a big difference in large arrays. And also, there's another issue which I'll get into later. So stay tuned for that. So another thing which you need to bear in mind, or which you could bear in mind, is just like be careful where you use Swift algorithms, because it's not great for everything. So these are the performance tests which I ran. You can see that it's hugely more efficient with a large array, like massively efficient, not just in memory, but so it's pretty much half the memory. It's also much faster, and there's no disk writes, so that's pretty good. Okay, so this is going to be an interactive part of the talk. I want to pose a question to the audience, and then like you to tell me what you think would happen. So I've got this bit of code here. Extension sequence where element numeric, sum the elements using this function here. And I've got this array here, and I want to do this function on that array. So tell me, what do you think happens? You can either put your hand up, put a comment in the questions, or you can, yeah, tell me what you think. I've got one message. Fatal error due to int8 overflow. I know. Okay. Anyone else? Don't be shy. You can ask, or you can say what you think. Okay, fine. So Douglas knows already, so that's I'm not going to ask him. But Maxime says fatal error due to int8 overflow. Let's see what happens if he's right. Okay. And you'd be surprised, actually. The thing with this is I looked on GitHub for code bases which use this function. So or something like this function. And it's really common, like thousands of code bases have this simple extension, and it's not in the standard library. So that could be a potential candidate for something to be implemented. Right, so I've got, right, so where am I going? So this is the tests, and we've got question 1, solutions. Okay, yeah, we'll get to that. Where's the code? Edge case, there we go. Right, so we've got an edge case here. This is the same function which we're defining as foresum, but foresum uses that sum which I showed you earlier. So one of them's a safe version, one of them's not. So let me think. Yeah, this is right. So this looks like the stuff we want to run. So let's run it, see if this works. Live demos, not great. Aha, that's what happens. So this is what happens. We get a runtime error, not a compile time error, which is quite bad because you can't catch it. You can't even catch it with try catch. It's an exe bad instruction, so that's really bad, and it won't even show up in your crash logs because it's quite a bad exception. So that's unsafe, and it crashes. So Maxime was right. He was absolutely right when he said it was going to overflow, and that's what's happened. So we've overflowed because we've added. Actually, I'll ask Maxime, why does he think it overflows? Or anyone else, if they want to pitch in, you can comment. 0 is not int8. That is true. That is true. But even if you do 1, let's see if that happens. That's a good point. Let's try it.
It's not that 0 is a particular type. The compiler will interpret that as whatever type is appropriate in the case you've got there.
So it's the same error. So you can see it's not related to that. But it's a good point. It's actually probably a bug actually in the code. But I wanted to do the sum, which is why I put 0. So I wanted to sum from 0. And if you add 1 to the starting value, that's not the sum. So that's just why it is like that. It's not ideal. Yeah, what was that? Sorry, who was speaking?
That was me, but maybe that wasn't appropriate. As in, if everyone started talking, it would be a nightmare.
Yeah, sorry, what did you say though? Was it that it's not 0?
Oh, I was just saying that, like, when you write 0 in your code, that isn't hard-coded as a particular type. That's a literal for 0, which the compiler will interpret as being, oh, we're using int 8 here, therefore you want an int 8 0. Just as in
right.
why it's not. Yeah, just trying to answer a reason.
Okay. Okay, I'm just looking at the comments. It goes to -72 and only 8 bits to store in it. Okay. Int 8 goes from -127 to 127, summing 100 plus 100 overflows. -100, -100. Because array has type int 8. 100 plus 28 will overflow int 8. Yeah, so Michael was right there. So if you have 8 bits and it's an int 8, that means that you have a maximum value of 127. So 128 will actually crash. I think that's right. This would have been easier having the input array on screen. Okay. I put it at the start, but I guess could have kept it on. Yeah, so that would work. So you can see that when reduce happens, it's an ordered collection. So somebody said it would go through -100, -100, but the first value was 128. So if I'd put the array first, you'd have seen that. So it goes through 100. This typecasts the whole array to int 8. So it detects that this value is int 8, and that means the whole array is going to be int 8, even though this, if it was on its own, would be just an int, and that wouldn't crash. But if you add int 8, which is unlikely, but if you do that, it will cause a crash, as you can see. Okay, and then actually the sum of that is -72. So if you add that together normally, if you did a safe sum, you would get -72, I think. So let me just show you that. So with the safe implementation, you get an array of all the elements in that array because they all add up to -72. So let's try that out now. Oh, it's already running. Okay. Right, I've got some messages. This would have been easy. Okay, if you change let array int, it would work. How come we don't get an error that array is not defined between int 8 and 8? Int 8 is a type of int. Is it the total that overflow? No, the total is not calculated. It's a runtime crash just on the first 2 elements. After the first array in the array is marked as int 8, I think all the literals, yeah, exactly. Yeah, Douglas got that right. Okay, so you can see it passed the test, which means that it didn't crash. And I've used a function here, which is in the standard library, actually. I mean, not the standard library, the algorithms package. I really like it, so I just implemented it again. So I've got a sequence which handles throwing assertions. So this would actually, if it was a regular error and I used xct assert equal, it would have been able to catch it because I've used this rethrows xct assert equals. And that's quite a nice little helper function. It's in the algorithms package if you want to check it out. But if you wanted to use xct assert equal objects, that would work, but it doesn't have a throwing support, so throwing function support. Okay, I think that's everything. Is that? So these are just some other tests. I'll go through these in a bit. It's not any means exhaustive, but it's just to show the idea. Okay, so that's that question. That's what happened. And this is a potential solution. So you may be wondering, how do you catch that error before it happens? And there is a function which is called adding reporting overflow. So when you add an element to a result, no, sorry. So this is a function which reports an overflow when you sum an element. So that's what this does for integers. So let's I think now would be a good time to show the safe code. Let me go back to here. So where's the safe code? Question one, sum array. So this is the sum elements which I talked about earlier. So this is the adding reporting overflow. You can check this out later. I'll put the code on GitHub. But the idea is that you limit it to signed integers, limit it to fixed width, you sum the elements, you start with each element, and it only works if the total overflow, when you sum the whole collection, it doesn't have a total overflow. So if you have a partial overflow when you're summing the elements, and the other elements, when you add them to it, it compensates for it, then it's okay, it doesn't crash. But because overflows are undefined, you can't use a regular sum to do it. So you have to use this special function, adding reporting overflow. There are actually lots of edge cases when you implement this. So this is not like, you can't put this in the standard libraries like that straight away, because there are lots of edge cases and stuff which I don't know about. So yeah, as you can just see like what happens. You've got a result which you start at 0. You've got an overflow Boolean which detects if you've got an overflow. You've got the total overflow count, and you see that as you keep adding the elements in the array, you get an overflow Boolean set, and you get the result added to itself, and then you get the overflow, total overflow. Yeah, so it could be a negative, so underflow, or it could be an overflow. So that's -1 for an underflow and 1 for an overflow. So you can see it's actually a total overflow to calculate both of them, and also to compensate. So if you have, yeah, so you can compensate it by making it, like if you have an overflow. So for example, if you have 100 plus 28, but the next value is a negative number, then you could compensate for the overflow and make it a total overflow of 0. And then if it's not 0, you do a precondition failure. That's a standard library thing. So you can, I just decided to do precondition, but you could do any kind of thing with that. Okay, that's the result. So you can see that that worked once we did it in ForSum. And just to see the solution in context again, it's summing all the arrays in each combination. Okay, and I've used arrays here just to make it simple. You could use sets, and technically you should use sets, because that is they're still valid. They're still valid solutions. Okay, so let's go back to slides. Right, there's the slides. Okay, so this, I'm going to go through like some common convenient functions which I really like in Swift algorithms. This one is really nice. Cycles. So you have a range and you want to enumerate the range 3 times. Rather than doing a nested for loop, you can just do dot cycle times 3. You can also do an infinite cycle without doing the times parameter. That's really handy. And then you've got unique. So this is really simple. You can just see it just finds all the unique elements, dot uniques, you understand it straight away. And the benefit of this is you preserve the ordering. So if you had 1, 3, 2 here, that would be 1, 3, 2 when you get the result back. And if it's 1, 2, 3 here, 1, 2, 3 would come back. But if you did this way, so you did let unique equals array set numbers, which is really common as well, that doesn't preserve the ordering. So just a little optimization for that. And then you can also do that on a predicate. So there's another function which lets you unique elements according to predicate. Right. Oh, I didn't say another thing. So, you know, when you're doing table views and you want to filter out elements or you want to remove duplicates. So for example, if you have a table view of contacts and you want to preserve the order of the contacts alphabetically or something like that, but you want to remove the duplicates, that would be a really good way of using this unique function. So that's really nice. There are ways you can use it if you think like table views and group table views, like ordering it by section. There's so many applications for this function, which I really liked. Okay, and combinations. So combinations allows you to, like the code showed in the first demo, we've got an array, we get all the combinations of size 2, and we print them all out. So that's pretty simple to understand. I think a really good use case for this, which I would use, is in unit tests. So PyTest, if you've used Python, has parameterized tests, which is something which XCTest doesn't have native support for. I really like parameterized tests. And I think that if you use combinations, it could be a really good way to cycle through all the input combinations. So if you have like a big potential set of combinations for input data, you just use this function to go through all the combinations and test all the edge cases rather than writing separate test cases for each one. And this is really nice because it's just like really robust. Okay. Cool. Right, what the next? So that is the order. Yeah, so this is, this returns an array. So if you've got a numbers array, it returns an array. That's the only thing. Oh, what's this? Demo. Right. Okay, so the next demo is about letter combinations. So the question is to calculate all the possible letter combinations for a given phone number. So I've added a digit phone number on the digit map on the right to see what digits map to what letters. So you can see that number 1 doesn't map to anything, 0 doesn't map to anything, 2 maps to ABC, 3 maps to DEF. So it's basically a hash map, which you could use for that, or a dictionary actually in Swift. So you'd use 2 to 9 inclusive, return all possible letter combinations that the number could represent, return the answer in any order. Okay, so let's look at an example. So you have digits 23, and the output would be AD, AE, AF, BD, BE, BF, CD, CE, CF. So that's really simple, and the order doesn't matter. Again, it's just a set of combinations. Right, so that is quite a misleading question because combinations in the question, you think you could use combinations for that. And for someone who's not used algorithms before, that's the first thing I did, actually. I tried to use combinations in every possible way using Swift algorithms, and I wasn't getting anywhere. I just couldn't make it work. So I realized that actually this problem is not a combinations question. So the idea behind this solution is actually graph theory. So you have to use a depth first or a breadth first search. So depth first is you process the deepest nodes in a graph first, and breadth first is you process each level of the graph systematically before doing the next level. So what I mean by that is if you think of this as a graph, you have 23. So each node, so each So 22 has A, B, or C as a value for each node in that graph. And from 2, you can get to D, E, or F. So you have a graph. So you have A, D is connected by an edge. A and D are vertices. And you have like a whole graph formed by that structure. So that's called a graph data structure. And the way you solve this is using graph traversal. So that's what this is called, where you enumerate the combinations. It's called a graph traversal. And the complexity of this is vertices, number of vertices, and number of edges. That's the runtime complexity. And then that's for both breadth first and depth first. And number of vertices on its own is the space complexity for both of them. And that's quite a lot of information. So I think now would be a good idea to see how to implement this. So I'll go back into Xcode. Okay, question 2, let's go to solution 1. Okay, right, so let's start from the top. Okay, so the first thing which I'm doing is I've got a local constant struct. It's an internal struct, and I've used a struct rather than an enum because I think I needed to use performance tests, and I wanted it to be allocated all in a stack to be consistent. So static let enum is on the heap. So that's just what this means, and why I've done it this way. Usually you would not bother about stack or heap allocation. I've used Swifty stuff, so I've done an extension on string. Oh, this doesn't look great. Let's do that. Okay, and then we've got a function which is the iterative solution. So there's a way to solve this with depth first search iteratively and recursively. And I'm going to use it without algorithms first, but the iterative solution is really optimized. So it's really efficient. So then what we've got an edge case first. So if the string is empty, there's no combinations. We generate the digit mappings. It's reversed. I'll get back to that later. But the idea is that you get a 2D array of you get a map inside an array. I think that's right. Yeah, I think that's right. So you've got local constants, which is a dictionary, and no, actually no, that is right. 2D array. This is a dictionary, and then this is an array, 2D array. So that's good. This is compact map. So if there's no digit mapping to that, it just ignores it, and then reverses the whole string. So you start at the last digit. Okay. And then you create the results for storing all the combinations. So you get the first digit option, and you map that to a string. Loop through each option set in the digit mappings. So the digit mapping would be this. So you loop through that. So you've got an option set, which is an array, and you need to generate the new results to add to the old results. So you've got a new results array, and you go results.forEach result in. So you append the results from previously, and you add the option in the option set. So yeah, and if this is like data structures, if you want to think about it in data structures, depth first search is a stack and breadth first search is a queue. So this is appending, and we've got a reversed. So the order is reversed as well. So like it does affect the order in which the results come in. So that's why I wanted to show you how you can play around with the reversed and the order of appending. So you can so this is essentially prepending. But because we're iterating backwards, it's it's still depth first search. And then you've got the end results, which you update after you've gone through all the results. And then you do that for each option set. And then after you've got all the results, you just return it. And you can see here again, it's very, very hard to read. It's quite hard. If I didn't put any comments, it would be quite hard to understand. And that's not a good thing, because if you're using an API, you want it to be easy to understand for other developers and yourself, in case you want to fix bugs or you want to update code. So it's not the most Swifty solution. Okay, right. So I've got here a, this is solution 2. So I've got a Swifty way to detect valid indexes. So I've got an extension on collection where element is a character. So that's a string. And then if the index is valid, that means it's less than the end index and it's greater than or equal to the start index. So that's just a way to not write that every time. So you can just do this function. And recursive function for DFS. So this is, you start with an empty array, you start with the start index. I'm iterating from the start this time, and I'm doing it recursively. So this will give different ordered results. And you can see that in the test as well. I'll show you the test in a bit. But that's a way to create a different graph technically. So does make a difference if you're doing things which need to be in an order. And then you've got generate all combinations. So you've got a recursive depth first search, and you've got a results array, you've got the current combination. So I'll explain what this is in a bit, but this is a helper function. And we've got a current combination which starts out as an empty string. So we start out with, so this is essentially traversing the whole graph and updating the results as you go through the whole graph. This is like a pure depth first search solution. And you can see that we've got the index, we're updating the index as we traverse the graph, and we're returning all the generated results. The traversal function, we've got an optimization for the in-out parameter. Detect the end of the traversal and append the current combination. So that is just once you've traversed to the deepest node, that means you've got a combination there. So once you've got a combination, like from the start or the root node to the deepest node, that means you can append that to the results. So we're updating the current combination as we're iterating through the graph. Quite complex, but this is how you'd actually do it properly. And then get the current digit, letters for the current digit, again using the digits map. And yeah, so we're going through the tree, we're going through the levels, we're updating the current combination, and then we're searching the next layer of the tree. And this keeps on going until you get to the end of the graph. So this, once you've done that function, you can return the results. Whew, that was a lot. So yeah, that is quite hard to read, quite hard to do. And the reason it's hard to do is because it's not implemented in algorithms. So the algorithms package doesn't have a good way to solve this problem. So it's another reason why, even though the first problem, we could solve it really easily with a combinations method, this structure, which we're using as a graph, so it's a non-linear data structure, which means that there are multiple ways to traverse it. So there's no defined order. So that's quite difficult to do with the way Swift is at the moment, but they've announced Apple that Apple have announced that in the future they want to add support for graph and other stuff. So we'll just have to wait and see what happens. But for now, they're just starting out, so they haven't got a good solution for this yet. So you can see that this solution is not very optimized as well. I've tried to just, I'm just trying to cook something up to see like how you could use Swift algorithms. So this is not optimized at all, but it's just a way to solve the problem another way. and it's kind of like a breadth first search. So I've got a help function starting at the start index, got the results, and I'm going through recursively all the combinations. Yeah, so same thing, base case. I mean, not the base, yeah, so that when you've iterated the whole graph, you return the results, get the current digit, generate current options, base case to initialize the results, generate the new results, update the results. This is the Swift algorithms function I wanted to show. So this is a way to iterate through two collections at the same time. So you've got a character in the current options, and you've got a results array. And rather than doing 4 character in current options, nest in, and then nesting after that closing brace, opening brace, a 4 result in results, you can just do update 4 character result in products, current option results. So that's quite nice. And update the results. Increment the tree level again. So this is the same kind of thing, recursively doing that again. Yeah, very hard to read. So now I'm going to show you the tests to see how it works. So like this is the way it's iterating through. So you can see like depth first search, how it's going to generate the combinations depending on how you start and how you implement it. So you're growing the graph, you're growing the traversal from the end index when you start from the end. So you start from, let's look at the question. This one, 923 is the start string. So you start with 9, then you go 2, then you go 3. But you saw that I reversed the array. So that affects how you generate combinations. So you see that we've got W changing first, then once you've got all those combinations tested for A and D, then you test for B and D, then you test for C and D, and you just like systematically go through that. So that's quite simple. And then this is a set. So this is because the ordering changed. And then this is recursive BFS. So this is kind of like another way to implement it using Swift algorithms. And I've added performance tests here as well. So you can, I'm not going to run these now because they take a long time, but these are how I generated the results on the slides. And you can run these later. I'll put a link to the repo after the talk, and you can play around and see how you find it. Okay. Right. So that's the results. So you can see that recursive wasn't as good as iterative, and they're roughly the same speed. And in summary, Swift algorithms is an excellent addition to the standard library. I think it makes it really good to write high performance applications. And while it works great for many problems, can't use it for everything. So you can't use it for everything. You can only focus on sequence types and clean up your code in many places. That's really nice. And you can use it in the Swift package manager right now, but it will be available in the Swift standard library later. And you can contribute as well online. So thanks for listening. That's my Twitter handle, Spidey Vitamins, and my GitHub link as well. And open to any questions.